Hello, and welcome to Late Physics, the channel where we dive into the most profound questions about our universe, from the big mysteries to the tiniest details that shape reality. Before we begin this journey through time, space, and philosophy, don't forget to like and subscribe. Your support helps keep these cosmic conversations going. And now, let's get started. Where are you watching or listening from today? Whether you're in the comfort of your living room, or perhaps somewhere else in the cosmos, it's amazing to think that no matter where you are, you're connected to the very same universe we're about to explore. The same universe that raises one of the most profound questions humans have ever asked. Why is there something rather than nothing? This question isn't just a curious thought experiment. It's at the heart of physics, philosophy, and the very essence of existence itself. From the birth of stars to the concept of time, from ancient philosophers to modern quantum scientists, this enigma has puzzled minds for centuries. As we embark on this journey, we'll explore ideas that challenge the boundaries of space and time, revealing how some of the brightest minds, both well-known and lesser-known, have approached the mystery of existence. Get ready for a deep dive into the cosmos, one that's not just about stars and particles, but the very fabric of reality itself. So grab your favourite beverage, sit back, and let's uncover why something exists when nothing seems like it could have been just as possible. Imagine for a moment that nothing existed. No stars, no planets, no galaxies, not even empty space. Nothing. It's a difficult thing to wrap your mind around. We live in a universe full of stuff: matter, energy, light, space, and time itself. So, the question arises, why is there something rather than nothing? At first glance, the answer seems simple. Things exist because of some underlying cause. But as we peel back the layers, we find that nothingness itself is much more elusive and puzzling than we might expect. Let's begin by considering the word nothing. What does it truly mean? The idea of nothing is a bit of a paradox. When we say there is nothing, what we often mean is that there is no thing, no object, no material, no energy, no space, no time. It's not the absence of a specific thing. It's the complete absence of everything. However, this idea runs into trouble when we step into the realm of quantum mechanics. According to modern physics, the vacuum, the seemingly empty space that stretches across the universe, is anything but empty. In fact, what we think of as nothing may not be nothing at all. Heinz-Dieter Rüder delved into this idea, pointing out that what we consider to be a perfect vacuum is actually a dynamic, buzzing sea of fluctuating quantum fields. Even in the emptier space, these fields are constantly fluctuating, creating pairs of particles that appear and disappear in the blink of an eye. These virtual particles pop in and out of existence, borrowing energy from the vacuum and returning it just as quickly. In this view, what we perceive as nothing is not the absence of anything, but a seething, unpredictable foundation for everything. This brings us to a key question. Does the universe, as we know it, need a cause to exist? And if it does, where did that cause come from? Many physicists, including the legendary John Archibald Wheeler, have grappled with this issue. Wheeler proposed the idea of a participatory universe, where the very existence of the universe is tied to the presence of conscious observers. In his view, the universe might not exist in any definitive way without the act of observation. This ties into the strange idea in quantum mechanics that the act of measurement, or even the possibility of measurement, determines the state of a system. Until an observer interacts with a quantum system, it can exist in multiple states at once. It's only when an observer participates in measuring or observing that the system collapses into a single state. Wheeler's view suggests that perhaps the existence of the universe itself isn't something fixed, but something that requires consciousness to bring it into being. It's a fascinating thought, that the universe may be as much about us as it is about everything else around us. It's not just that consciousness is something that exists within the universe. It might be essential for the universe to exist in the way that we experience it. But let's not get too far ahead of ourselves. The idea of nothing is still waiting for us to dig deeper into its nature, and for that we turn to the ideas of Erwin Schrödinger, one of the founding fathers of quantum mechanics. Schrödinger, best known for his famous thought experiment involving a cat that is both alive and dead until observed, proposed that nothing could actually be a state of pure potential. In his view, before anything becomes something, it exists in an undetermined probabilistic state, an idea central to quantum theory. This idea is not as strange as it sounds. In fact, it is a fundamental feature of the quantum world. Particles don't have definite properties until they are observed. They exist in a state of possibility, where their location, momentum, and even their very identity are not fixed but probabilistically spread out. This concept of pure potential, where something only becomes real when observed or measured, challenges our classical ideas of a beginning in a universe that only exists because something caused it to be. As we take this one step further, let's explore the implications of quantum fluctuations. Steven Weinberg, a Nobel Prize-winning physicist, contributed to our understanding of these fluctuations by showing that, in the absence of any particles or radiation, quantum fields still fluctuate. These fluctuations are not just mathematical artifacts, they have real physical consequences. In a sense, these fluctuations can be thought of as seeds of reality, from which particles and forces arise. So it seems that even when we think we're in the presence of nothing, we're actually surrounded by a quantum field constantly in motion, full of virtual particles that flicker in and out of existence. These fleeting events have a profound influence on the structure and behavior of the universe at its smallest scales. And yet, the strange paradox remains. These phenomena are often described as nothing, when in reality, they are something. They are the very fabric of reality, interacting, fluctuating, and shaping the universe we see and feel every day. These ideas challenge our usual understanding of nothingness. It turns out that nothing is far more complicated than we think. It's not the absence of anything. Rather, it's a concept that stretches the limits of our imagination and forces us to reconsider the very foundations of existence itself. It's a concept that has taken physicists, philosophers, and thinkers from all walks of life on a journey to understand the deepest mysteries of the cosmos. And as we continue exploring, we might find that the answer to why there is something rather than nothing is far more subtle, far more connected to the mysteries of space, time, and consciousness than we ever expected. So the next time you gaze at the stars or think about the origins of the universe, remember, nothing may not be the empty void we imagined it to be. It might just be the most surprising something of all. The Big Bang Theory is one of the cornerstones of modern cosmology. It's the idea that the universe began as an incredibly hot, dense point around 13.8 billion years ago and has been expanding ever since. This idea explains much of what we observe in the universe today: the cosmic microwave background radiation, the distribution of galaxies, and the abundance of light elements like hydrogen and helium. It paints a picture of the universe starting from a single, incredibly small point, often referred to as a singularity. However, what if the Big Bang wasn't actually the beginning? What if the universe didn't just start from nothing at that moment, but rather, it's part of a much longer, ongoing process, a cycle of creation and destruction stretching back and forward infinitely? This is where some alternative theories come into play, challenging the idea of the Big Bang as the beginning. These theories introduce fascinating concepts, from eternal cycles to cosmic reproduction. One of the most intriguing ideas comes from Roger Penrose, a physicist and cosmologist known for his work in general relativity. Penrose developed a theory called conformal cyclic cosmology, or CCC for short. According to CCC, the universe doesn't just begin and end in a singular event, but rather it goes through an infinite number of cycles, each one beginning with a Big Bang-like event and ending in a state of infinite expansion. Penrose's theory suggests that each cycle of the universe, each aeon, is followed by the next, with the end of one universe seamlessly transitioning into the beginning of the next. The key feature of CCC is that the Big Bang itself isn't a one-off event, but part of a repeating process. When the universe reaches a state of extreme expansion, with galaxies and matter spread so thin that they no longer interact, it reaches a kind of final, conformal state. In this state, time and space themselves stretch and flatten in a way that allows the universe to reset. A new Big Bang follows, and the cycle begins again. What makes this idea even more intriguing is how it handles the concept of the beginning. In Penrose's view, the Big Bang isn't a beginning at all. Instead, it's the latest in an infinite series of beginnings and endings, all linked by a process that transcends any single moment of creation. In this framework, there's no true beginning or end, just a series of transformations stretching back infinitely. This perspective challenges our everyday understanding of time and cosmology. because the beginning of the universe, as we traditionally think of it, might not have ever existed. Now let's look at another theory that brings a different twist to the idea of the universe's origins: Lee Smolin's theory of cosmological natural selection. Smolin, a theoretical physicist, proposed a fascinating idea: that universes may reproduce, much like organisms in the natural world. According to Smolin, new universes might be born inside black holes. When a black hole forms, the intense gravitational forces at its core might give rise to a new universe, one with slightly different physical laws. In this model, the universe we live in could be just one of many, each universe spawned from a black hole in another. Universes in this sense could be competing in a Darwinian way. Universes with physical laws that lead to stable, long-lasting systems might be more likely to produce black holes and, in turn, new universes. Universes with laws that don't allow for the creation of black holes would be less likely to reproduce. Over time, the physical laws that favour the creation of black holes would dominate, creating a form of cosmological evolution. Smolin's theory brings a new perspective to the idea of existence. Instead of a singular Big Bang event marking the beginning of the universe, he suggests that the birth of new universes could be a continual process, tied to the creation of black holes in our own universe. It's a concept that suggests our universe could be part of a much larger, evolving cosmic system, with each new universe born out of the collapse of its predecessor. But what if the Big Bang itself wasn't the beginning, not just of one universe, but of all of existence? This brings us to the theory of the multiverse. The multiverse is a collection of different, potentially infinite universes that may each have their own distinct set of physical laws. The idea comes in many flavors, but some of the most compelling theories are those put forward by cosmologists like Andrei Linde and Alexander Vilenkin, who both argue that the Big Bang could be just one phase in an ongoing process of creation. Linde, who is often associated with the idea of chaotic inflation, proposed that the universe we see today is part of a larger, never-ending process of inflation. In Linde's model, the universe expands rapidly in its earliest moments, faster than the speed of light, creating the vast flat cosmos we observe today. However, this expansion doesn't happen everywhere uniformly. In some regions, inflation continues, creating new bubbles of space-time, each one developing into its own separate universe. These universes, or bubbles, each have their own set of physical laws and constants. Some may have conditions that allow for life, while others may be inhospitable. In this version of the multiverse, the Big Bang wasn't a single unique event, but rather the latest in an infinite process of inflationary universes. Each universe could be separated by vast expanses of space-time, and may even have completely different laws of physics. This idea turns the Big Bang on its head, suggesting that our universe is just one bubble in a vast multiverse filled with countless other bubbles, each with its own cosmic history. Another variation on the multiverse theory, proposed by Alexander Vilenkin, is known as eternal inflation. According to this model, inflationary expansion didn't just happen once, at the moment of the Big Bang. It has been happening continuously, creating new universes all the time. In Vilenkin's view, the universe we see today is just one of countless others, each constantly being spawned through an ongoing process of inflation. In this sense, the Big Bang was not the origin of the universe, but merely the beginning of a new bubble of space-time within the larger eternal process of cosmic inflation. Both of these theories suggest that the Big Bang was not the start of everything, but rather part of an ongoing eternal process, one that may continue indefinitely, with new universes continually being born. What all these theories have in common is the idea that the universe we know may not have been the first universe, and the Big Bang might not have been the true beginning of all things. Whether through the infinite cycles proposed by Penrose, the evolutionary process of universes suggested by Smolin, or the ever-expanding multiverse described by Linde and Vilenkin, these ideas open up the possibility that the universe, and everything in it, might be part of a much larger, more complex picture, one that defies our conventional understanding of time, space, and origin. So while the Big Bang may have been the beginning of the universe we see today, it could very well be just one chapter in an infinite cosmic story, a story of creation, destruction, and rebirth that stretches beyond our wildest imagination. The world we live in, the universe we observe, seems so stable, so predictable. Yet, beneath the surface there is an entirely different reality, a strange, uncertain realm governed by the laws of quantum mechanics. This is the world of the very small, particles, waves, and fields that don't behave in ways we can easily understand, much less replicate in our everyday experiences. To say it is strange would be an understatement. At the heart of quantum mechanics lies the idea that particles don't exist in one fixed state until they are measured. Instead, they exist in a superposition of multiple possibilities, each one with a certain probability. This isn't just a theoretical idea. It has been confirmed by countless experiments. In fact, it's one of the most verified concepts in all of science. The implications of this quantum weirdness have fascinated scientists for over a century, and perhaps no one has pushed these ideas further than David Deutsch. Deutsch, a physicist and advocate of the many worlds interpretation of quantum mechanics, believes that quantum mechanics offers a view of reality that is far more expansive than our usual understanding. In the many worlds interpretation, every time a quantum event occurs, whether it's the spin of an electron or the path of a photon, it doesn't just choose a state. Instead, all possible outcomes occur, each in its own parallel universe. In this view, the universe we experience is just one of many that exist simultaneously, each branching out from every possible quantum decision. Imagine for a moment that every time you make a choice, no matter how small, an entirely new universe is created where you made the other choice. You might take one path, but in another universe you might have gone down a different road entirely. In this interpretation, the idea of possibilities becomes far more literal. The universe isn't just a single path. It's a network of interconnected possibilities, each one unfolding simultaneously in a kind of cosmic tree of alternate realities. While the many worlds interpretation might sound like science fiction, it is, at its core, a direct consequence of quantum mechanics. It solves some of the paradoxes of quantum theory by removing the need for wave function collapse. In the standard interpretation, quantum particles exist in a superposition, both here and there, until measured. At that moment, the wave function collapses, and the particle chooses a state. The many worlds interpretation says instead that all of these possibilities happen, just in different, non-interacting worlds. Anton Zeilinger, an Austrian physicist known for his work on quantum entanglement, has further demonstrated the strange implications of quantum theory. One of the most famous phenomena in quantum mechanics is called entanglement. When two particles become entangled, their properties are linked in such a way that the state of one particle instantly influences the state of the other, regardless of the distance between them. It's as if information travels faster than the speed of light, which is something that we thought was impossible according to Einstein's theory of relativity. Zeilinger's experiments in the late 20th century helped confirm that entanglement is not just a theoretical concept, but something real that we can observe and measure. In one of his landmark experiments, he demonstrated that two entangled photons could affect each other, even when separated by vast distances, something Einstein famously called spooky action at a distance. This seemingly violates our usual understanding of how information can travel through space, suggesting that reality at the quantum level doesn't conform to the rules we experience in the macroscopic world. Quantum entanglement has far-reaching implications for how we think about the nature of reality itself. If particles can be so intimately connected, so that changes to one instantaneously affect the other, no matter the distance, it suggests that the universe is far more interconnected than we might have thought. The classical idea of objects existing independently in space and time starts to break down when we move to the quantum realm. This has led to some fascinating philosophical ideas, including those proposed by Roger Penrose, a physicist and mathematician renowned for his work in cosmology and quantum mechanics. Penrose has suggested that consciousness itself may be a product of quantum processes in the brain. In his book The Emperor's New Mind, he proposed that the strange behavior of quantum mechanics could explain the mystery of consciousness, something that classical physics struggles to account for. Penrose's hypothesis, known as orchestrated objective reduction, OR, posits that quantum coherence occurs within the brain's microtubules, tiny tube-like structures inside neurons. He suggests that these quantum processes might be linked to our conscious experience. Unlike classical processes, which are predictable and deterministic, quantum processes are probabilistic and uncertain. In Penrose's view, it's this uncertainty, this fundamental indeterminacy, that allows for the subjective experience of consciousness to emerge. Consciousness, then, could be seen not as a byproduct of classical brain processes, but as a direct result of the very quantum fabric of reality itself. Now, let's broaden our scope even further and explore one of the most exciting and potentially mind-bending theories to emerge in the 20th century: string theory. Brian Greene, a leading theoretical physicist and author, has championed the idea that the fundamental building blocks of the universe are not particles, as we traditionally think, but tiny vibrating strings of energy. According to string theory, these strings vibrate at different frequencies, and the specific frequency of vibration determines the type of particle they create. This theory suggests that all the forces of nature, from gravity to electromagnetism, are manifestations of different vibrational states of these fundamental strings. String theory doesn't just introduce new ideas about particles, it also predicts the existence of extra dimensions. While we experience the world in 3 dimensions of space and 1 of time, string theory proposes that there may be additional spatial dimensions, perhaps up to 9 or 10 in total, hidden from our view. These dimensions are compactified, meaning they are curled up so small that we can't detect them with our current instruments, but they may be crucial in understanding the fundamental forces of nature, including gravity, which string theory ties to the behavior of strings. These extra dimensions could also provide a potential solution to one of the biggest challenges in physics, reconciling general relativity, which explains gravity, with quantum mechanics, which governs the very small. In essence, string theory may offer a framework that unifies all of the fundamental forces in nature, providing a theory of everything. What's truly fascinating about string theory, and theories like it, is that they provide a possible answer to the most profound question of all: why is there something rather than nothing? According to string theory, the universe we observe may simply be one of many possible configurations of strings and dimensions, each vibrating in a slightly different way, and each giving rise to a different universe with its own set of laws. The nature of reality itself could be far more complex and far more interconnected than we ever imagined. The implications of these ideas are staggering, from quantum mechanics, which tells us that particles don't exist in a fixed state, but instead exist in superpositions of possibilities, to the theory of the multiverse, which suggests that our universe might be one of countless others. We see that the universe is far more mysterious and dynamic than we can observe in our everyday lives. The nature of reality itself, from the smallest quantum particles to the largest cosmic structures, might be governed by principles we have only begun to understand. In this strange and beautiful world of quantum mechanics and beyond, reality isn't as fixed and certain as we once thought. It's fluid, probabilistic, and deeply interconnected. And it might just hold the answers to why something exists in the first place. What if the universe itself is a giant computation, a vast, intricate process of information being processed, stored, and transmitted at every level, from the most basic particles to the largest cosmic structures? It's an idea that might seem abstract, but it's one that's gaining more attention in the realms of physics and philosophy as scientists explore the role of information in shaping reality. One of the most intriguing ideas in this realm comes from John Archibald Wheeler, a theoretical physicist who proposed the bold theory that it from bit, in other words, that everything in the physical universe emerges from information. Wheeler's idea was revolutionary. Instead of seeing physical objects as the fundamental building blocks of the universe, he suggested that information might be the most fundamental aspect of reality. According to Wheeler, all the forces, particles, and fields that we observe in the universe could be seen as manifestations of underlying informational structures. Wheeler's it from bit theory implies that at the most basic level, the universe is not a collection of solid objects, but rather a vast, intricate system of information processing. He suggested that information is at the core of everything, just as in computer science, where the binary digits 0 and 1 form the basis of all digital information. The universe itself might be built from bits of information, fundamental units that determine the behavior and properties of all things. This is not just a philosophical idea. It has real consequences for how we think about the structure of the universe and the nature of reality itself. In this view, the physical universe might be an emergent phenomenon, arising from the interaction and organization of information at deeper levels. Instead of thinking of the universe as a set of objects interacting in space and time, Wheeler's theory encourages us to think of it as an evolving process of information being encoded, decoded, and transformed. From this perspective, everything, whether it's a star, a planet, or even the laws of physics, could be seen as a kind of informational pattern, evolving over time in response to certain rules and constraints. But what does this mean for our understanding of existence? If the universe is, at its core, made of information, then it might be governed by rules that are more akin to computation than to the classical laws of physics we're used to. To explore this idea further, we can turn to Max Tegmark, a physicist and cosmologist who proposed the mathematical universe hypothesis. According to Tegmark, the universe isn't just made up of information, it is information. Specifically, it is a mathematical structure. Tegmark's hypothesis takes the idea of it from bit one step further, suggesting that the universe is not just a collection of bits of information, but is actually a mathematical object, an abstract structure that can be described entirely by mathematics. In his view, every aspect of the universe, from the formation of galaxies to the behavior of subatomic particles, is governed by mathematical laws. These laws don't just describe reality, they are reality. The universe, in this view, is not something that merely follows mathematical principles, it is itself a mathematical entity. What makes Tegmark's hypothesis particularly interesting is its far-reaching implications. If the universe is a mathematical structure, then it follows that everything within it, everything we perceive, from the smallest particles to the largest cosmic scales, is part of a larger mathematical framework. This means that our reality might not be as physical as we think. Instead, it could be more like a computer simulation, a program running on the hardware of the universe. In this sense, the idea of the universe as a computation becomes not just a metaphor, but a literal description of how the cosmos works. Building on this idea, Gregory Chaitin, a computer scientist and mathematician, introduced the concept of algorithmic information theory. Chaitin's work focused on the idea that the universe might be fundamentally describable by simple programs. In algorithmic information theory, the complexity of a system is measured by the length of the shortest program that can describe it. Essentially, the more information you need to describe something, the more complex it is. Chaitin's ideas suggest that the universe at its core might be a very simple program, one that generates the complex phenomena we observe as part of its unfolding. This simplicity is key to understanding the universe as a computation. If the universe can be described by a simple program, then it implies that reality itself is computationally efficient, perhaps even elegant in its underlying design. This theory doesn't just provide a new way of thinking about the universe, it offers a potential bridge between the physical world and abstract information theory, opening up new avenues for understanding the laws of physics. Now, let's take this one step further by exploring the connection between quantum mechanics and computation. This connection is made clear in the concept of quantum information theory, which suggests that information is not just a passive quantity in the universe, but something actively involved in the fabric of reality. Quantum computers, which use the principles of quantum mechanics to perform computations, offer a glimpse into how information might be processed at the quantum level. In a quantum computer, information isn't stored in traditional bits like in classical computers. Instead, it's stored in quantum bits, or qubits, which can exist in multiple states simultaneously due to the phenomenon of superposition. This allows quantum computers to process enormous amounts of information in parallel, offering the potential for solving problems that are currently beyond the reach of classical computers. But quantum computers don't just process information, they also generate it, and in doing so they reveal how the fabric of reality itself might be structured by information. This connection between quantum mechanics and information theory suggests that information could be a fundamental ingredient of the universe. Quantum entanglement, the strange phenomenon where particles become instantaneously linked regardless of distance, can be thought of as a kind of information exchange between particles. This challenges our classical understanding of space and time, showing that the universe might not be as physical as we perceive it, but rather a network of interconnected information, flowing and interacting in ways that transcend the traditional limits of space and time. By combining these ideas, the concept of the universe as a mathematical structure, the idea of information as the foundation of reality, and the insights from quantum computation, we begin to see a new, more abstract picture of the universe. Far from being a static physical entity, The cosmos could be an ever-evolving computational process, where information flows and evolves according to mathematical principles. This view invites us to consider the possibility that the universe is not just a collection of objects, but a vast, intricate computational system, processing and generating reality itself. As we look deeper into the role of information in the universe, we might find that the boundaries between the physical and the abstract begin to blur. Information, it seems, may not just be a tool for understanding the universe, it may be the very essence of existence itself. And as our understanding of quantum mechanics and computational theories continues to evolve, we may be on the brink of discovering that the universe is far more like a giant cosmic computer than we ever imagined. Black holes have long captivated our imagination. These mysterious regions of space, where gravity is so strong that not even light can escape, challenge our understanding of the universe in profound ways. They are, in many respects, the ultimate test for our theories about the nature of space-time and the very fabric of existence. And, as strange as it may sound, black holes may offer us a window into the deepest questions about the origins of the universe, the nature of reality, and perhaps even the existence of other universes. One of the most fascinating contributions to our understanding of black holes comes from Roger Penrose, who proposed a radical idea about what might happen at the heart of these cosmic giants. According to Penrose, black holes are not just places where matter is compressed into an infinitely small point, a singularity, but they may actually serve as gateways to other universes. This idea arises from his work on the Penrose singularity theorem, which shows that, under certain conditions, the formation of a black hole leads to the creation of a singularity, a point where space-time itself breaks down. Penrose took this further, suggesting that black holes could be more than just cosmic graveyards for dying stars. He theorized that the singularities at the centers of black holes could be connected to the birth of new universes, forming a kind of bridge between different parts of the multiverse. In his view, when a black hole forms, the gravitational collapse could create a singularity that acts as a portal to another universe, much like the Big Bang might have been a transition from one cosmic cycle to another. This would mean that the universe we know could be just one of many, with black holes acting as conduits for the transfer of matter and energy between them. This idea is mind-bending and profoundly important, because it suggests that the universe we observe might not be a one-off event, but part of an eternal process that could span across multiple universes, each born from the collapse of a black hole in a different universe. In this way, black holes might not just be places of destruction, but seeds for new beginnings, creating a never-ending cycle of birth and rebirth across the cosmos. Yet, as we explore the mysteries of black holes, another question arises: what happens to the information contained within them? The concept of the information paradox was introduced by Stephen Hawking in 1974, and it remains one of the most perplexing issues in modern physics. The paradox arises from the fact that, according to quantum mechanics, information cannot be destroyed. But what happens to the information that falls into a black hole? According to classical theory, anything that crosses the event horizon, the boundary beyond which nothing can escape, disappears from the observable universe, seemingly erasing all information about it. This leads to a deep conflict between general relativity, which governs the behavior of gravity and black holes, and quantum mechanics, which governs the behavior of particles at the smallest scales. If information is truly lost inside a black hole, it would violate the principles of quantum mechanics. In response to this, Hawking proposed that information might be lost forever, creating a fundamental tension in our understanding of the laws of physics. However, in the decades since, there has been growing evidence suggesting that this information may not be lost after all. In fact, a number of physicists, including Juan Maldacena and Jacob Bekenstein, have worked on ways to reconcile the idea of black holes with the principles of quantum mechanics. Bekenstein, in particular, proposed that the amount of information that can be contained within a black hole is proportional to its surface area, not its volume. This insight led to the development of the holographic principle, a revolutionary idea in theoretical physics. The holographic principle suggests that the information contained in a three-dimensional volume of space, such as a black hole, can actually be described by information encoded on the two-dimensional surface surrounding that volume. In other words, the universe we experience with its 3 dimensions of space and 1 dimension of time might actually be a projection of information stored on a 2-dimensional surface, much like a hologram. This idea was proposed by Carlos Castro, who suggested that black holes might be a perfect example of this principle in action. The surface of a black hole, the event horizon, might contain all the information about the objects that have fallen into it, encoded in a way that we cannot yet fully understand. The holographic principle has profound implications for our understanding of the universe. It suggests that space itself may not be the fundamental entity we think it is, but rather a projection of deeper, more fundamental information. This challenges our very notion of what it means for something to exist. If the three-dimensional world we experience is just a projection of two-dimensional data, then perhaps everything we perceive as physical reality, matter, space, time, might be just an illusion, a trick of the light created by the underlying informational structure of the universe. This brings us to the connection between black holes, quantum mechanics, and the fundamental nature of reality. One of the most exciting developments in theoretical physics in recent years has been the recognition that black holes might hold the key to understanding quantum gravity, the theory that seeks to unify general relativity with quantum mechanics. Maldaceno's work on the ADS/CFT correspondence in the late 1990s, which established a connection between a type of black hole solution in anti-de Sitter space and a conformal field theory, was a major breakthrough in this area. His work suggested that quantum gravity, the theory that governs the very fabric of space-time, might be understood through the lens of quantum information theory and the holographic principle. Maldaceno's research also hinted that the strange properties of black holes, particularly their connection to quantum mechanics, could be the key to understanding how information is preserved in the universe. By studying black holes, scientists are beginning to realize that the fundamental nature of reality might not be physical in the traditional sense, but rather informational, encoded in a way that we can only begin to comprehend. In essence, black holes may be more than just the mysterious destructive objects we once thought them to be. They could be windows into a deeper understanding of existence itself, revealing the underlying structure of the universe and providing answers to some of the most profound questions in physics. From the information paradox to the holographic principle and beyond, black holes are forcing us to rethink the very nature of space, time, and reality. As we continue to explore these enigmatic objects, we may find that they hold the keys to unlocking some of the deepest mysteries of the cosmos. The universe we live in is a place of incredible complexity, a place where the conditions that support life as we know it, seem finely tuned. It's almost as if the universe is designed specifically to allow life to emerge, with physical constants and laws that just happen to be exactly right for the existence of stars, planets, and living organisms. But is this fine-tuning the result of random chance? Or could there be another explanation? Is it possible that the universe is not the product of sheer accident, but instead the outcome of some deeper process? One of the most striking arguments that challenges the idea of randomness comes from Roger Penrose, who proposed what's known as the strong anthropic principle. According to Penrose, the universe's fine-tuning is not just a coincidence, but is in fact necessary for life to exist. He argued that the physical constants and laws of nature are not just random, but appear to be precisely set to allow for the formation of stars, galaxies, and life itself. In his view, the universe has chosen the values for these constants, not by chance, but in a way that enables the emergence of life and consciousness. Penrose's strong anthropic principle implies that the universe's laws may be set by some inherent necessity, not just by accident or chance. It suggests that the very fact that life exists is not a fluke, but a requirement of the universe's structure. In essence, the conditions that allow for life may be built into the fabric of the universe itself, as though life were meant to arise in such a universe. But Penrose's ideas aren't the only perspective on the fine-tuning of the universe. John Barrow and Frank Tipler, two other well-known cosmologists, also contributed to what is known as the anthropic principle. Their interpretation is a little different, arguing that the universe is indeed fine-tuned, but they propose that this fine-tuning might not be for life itself, but for the development of any life, given the conditions. Barrow and Tipler argue that the universe's physical constants are simply ideal for life, but it doesn't necessarily mean that life was the purpose of the universe. Instead, the universe might simply have the right set of laws for life to emerge, and life, once it appears, fits into those laws. According to this view, there's no grand design behind the fine-tuning. it's just a consequence of the universe's physical properties. In a similar vein, Lee Smolin introduced the concept of cosmological natural selection, which offers yet another twist on the fine-tuning argument. Smolin's idea is based on the notion of a multiverse, a collection of multiple universes, each with its own set of physical laws. In Smolin's view, universes are not randomly created, but rather they reproduce in a way that is similar to biological evolution. When a black hole forms in one universe, it might give birth to a new universe, with slightly different physical laws. Over time, universes that produce black holes and have conditions conducive to life are more likely to reproduce by spawning new universes. These new universes would carry the same physical laws that allow for black holes to form, creating a cycle where universes that support life are favoured in the long run. Smolin's cosmological natural selection theory presents an interesting challenge to the idea of a random, chance-driven universe. In his model, the laws of physics aren't just a product of random chance, but the result of a process of selection. The universe we live in, with its finely tuned conditions, could be the product of this process, with physical laws that are not random but shaped over time to allow for the emergence of life. But what if the fine-tuning we observe is the result of something even grander than a single universe? This brings us to the multiverse theory. If our universe is just one of many, the question of fine-tuning becomes even more complicated. David Deutsch, a physicist known for his work on the multiverse, has argued that the very concept of a multiverse may help explain the apparent fine-tuning of the universe. According to Deutsch, the multiverse is made up of countless universes, each with different physical laws. Some of these universes may have laws that do not allow for life, but others will have the right conditions for life to emerge. The existence of multiple universes, each with different laws, means that the fine-tuning of our universe might simply be the result of a probabilistic process, where universes with laws that allow for life are far more common than those without. In this view, fine-tuning is not a unique feature of our universe, but a consequence of a multiverse that contains a vast array of possible worlds, with each universe randomly picking its own set of laws. Some universes will be fine-tuned for life, while others may never produce conditions that could support life. The fact that we find ourselves in a universe that is finely tuned is simply a matter of statistical probability. Out of all the possible universes, we just happen to live in one that allows for life. This idea of multiversal fine-tuning offers a way to think about the universe's fine-tuning without invoking design or purpose. Instead of seeing the universe as having been specifically set up to support life, the multiverse theory suggests that life arises in universes simply because such universes are likely to exist. The apparent fine-tuning of our universe is simply the result of being part of a larger probabilistic landscape where many possibilities coexist. The question of whether our universe is fine-tuned for life, and whether that fine-tuning is the result of chance, necessity, or design, is a deeply philosophical one. On one hand, the universe seems perfectly crafted to allow life to emerge, and this has led many scientists and thinkers to suggest that the conditions we observe are not random, but rather are the product of some deeper principle. Whether that principle is the result of a multiversal process, a cosmic selection mechanism, or even a deeper as yet unexplored principle of nature, the fine-tuning argument challenges us to think about the universe in ways that stretch beyond the realm of traditional physics. The multiverse theory, in particular, provides an intriguing explanation for the apparent fine-tuning of the universe. By proposing that we live in just one of many possible universes, each with different laws, the multiverse theory offers a probabilistic approach to the question of existence. Rather than seeing the universe as a finely tuned system with a specific purpose, the multiverse suggests that we are simply one of many worlds that emerge from a vast cosmic lottery. In the end, the fine-tuning of the universe raises more questions than answers. Is the universe we live in the result of chance, necessity, or design? Are we truly living in a universe that is finely tuned to support life, or is it simply one among many possibilities? The answer may be more complex than we can currently fathom, but the search for an answer will continue to push the boundaries of science and philosophy, inviting us to explore the very nature of existence itself. Consciousness, the very experience of being aware, is one of the most profound mysteries we face. It's something we all experience intimately, yet when we try to understand how it fits into the larger picture of the universe, things become murky. Is consciousness just a byproduct of the physical world, something that emerges from the complex interplay of neurons and chemical signals in our brains? Or could it be more fundamental, an intrinsic aspect of reality itself shaping the very fabric of the universe? One of the most famous philosophers of mind, David Chalmers, has grappled with these questions, and in doing so he brought attention to what he calls the hard problem of consciousness. This is the question of why and how subjective experience arises from the physical processes of the brain. We know that when certain neural circuits fire, we perceive certain things, colours, sounds, thoughts. But why does the firing of these circuits feel like something to us? Why do we have an internal experience at all, rather than simply responding to the world in an entirely mechanistic way? Chalmers' hard problem goes beyond asking how consciousness works. It asks why we have conscious experiences in the first place. Could it be that consciousness is necessary for the universe to exist in the way that we experience it? Or is it merely a byproduct, an emergent property of matter, like the way a complex pattern arises from simple rules in a computer simulation? One intriguing possibility comes from Giulio Tononi, who proposes an entirely different framework for understanding consciousness. Tononi's integrated information theory, or IIT, suggests that consciousness is not merely an emergent property of complex systems, but rather a fundamental property of the universe itself. According to IIT, consciousness arises whenever a system can integrate information in a unified way, creating a coherent experience of being. Tononi's theory suggests that consciousness is a measure of how much information a system can process and integrate. The more information that is integrated into a unified whole, the more conscious that system is. In this sense, consciousness is not something that simply emerges at a certain level of complexity. It is an intrinsic property that arises wherever there is a sufficiently integrated system of information. This challenges our traditional view of consciousness as something that's simply added on to complex physical systems. Instead, consciousness might be woven into the very fabric of reality, as essential to the structure of the universe as space or time. While Tononi's theory offers a way to think about consciousness as fundamental, Roger Penrose took a more radical approach by linking consciousness to quantum mechanics. Penrose, who is perhaps best known for his work in general relativity and black holes, proposed that consciousness could be related to quantum processes in the brain. In his controversial theory of orchestrated objective reduction, or QOR, Penrose suggested that the brain's microtubules, tiny tube-like structures within neurons, could serve as quantum computers, processing information in a way that is not governed by classical physics, but by the rules of quantum mechanics. According to Penrose, quantum coherence occurs in these microtubules, allowing them to perform calculations in parallel, using the probabilistic nature of quantum mechanics. Penrose argued that this quantum process could be the key to understanding consciousness, suggesting that consciousness arises not just from complex neural networks, but from the quantum processes that occur within the brain. These quantum processes, in Penrose's view, might explain why we experience conscious awareness, why it feels like something to be us, and why we have subjective experiences at all. Penrose's theory is certainly bold, and it challenges our classical understanding of the brain. It also raises the question of whether consciousness could exist beyond the brain entirely. Could consciousness be a fundamental part of the universe, present at every level of existence, not just confined to human minds? Penrose's work invites us to think about consciousness as something more than a product of brain activity. It suggests that it may be intricately tied to the fundamental processes of the universe itself. Now, let's look at a perspective that takes consciousness even further as the foundational aspect of reality. Bernardo Kastrup, a philosopher and researcher in the field of consciousness studies, proposes a radical view called philosophical idealism. In this view, consciousness is not a product of the brain or the physical world, but the very substance of reality. According to Kastrup, everything in the universe, from particles to galaxies, is ultimately a manifestation of consciousness. The physical world is not the foundation of reality. It is the result of consciousness interacting with itself. Kastrup argues that what we perceive as the material world is in fact a kind of thought, within a larger, universal consciousness. In this framework, the universe itself is a dreamlike manifestation of a singular, all-encompassing consciousness. Our individual consciousnesses are fragments of this larger mind, experiencing the world as we perceive it. According to philosophical idealism, the physical world, what we call matter, is secondary, a result of the mind's perception and interpretation of itself. This view contrasts sharply with materialism, which holds that consciousness is a byproduct of physical processes. Instead, Kastrup's idealism places consciousness at the very center of reality, with the physical world being its expression. Kastrup's work invites us to rethink our assumptions about what's real. If consciousness is the foundation of reality, then the material world we experience may be an illusion, a projection of the underlying consciousness. This doesn't mean that the physical world doesn't exist. It simply means that what we perceive as physical is at its core a product of the mind. This theory opens up fascinating possibilities for understanding the nature of existence itself. If consciousness is the true substance of reality, then perhaps everything we experience is shaped by our awareness in ways we have yet to fully understand. Taken together, these ideas, Penrose's quantum consciousness, Tononi's integrated information theory, and Kastrup's philosophical idealism, suggest that consciousness might not be just a passive observer of the universe. Instead, it might be the very force that shapes reality, influencing the structure of the universe in ways we are only beginning to comprehend. From the quantum processes in the brain to the very fabric of existence, consciousness may be intimately tied to the way the universe functions. The question of whether consciousness shapes reality is not just a philosophical one. It touches on the deepest mysteries of physics, cosmology, and our own existence. Whether consciousness is a byproduct of the brain, a fundamental feature of the universe, or the very fabric of reality itself, it remains one of the most intriguing questions in science and philosophy. As our understanding of the universe deepens, we may find that the answer to this question holds the key to unlocking the true nature of existence itself. Time and causality are two of the most deeply ingrained concepts in our understanding of the universe. We move through time, experience events in a linear sequence, and assume that one thing causes another. But as we look deeper into the nature of the universe, questions arise. Are time and causality truly fundamental aspects of reality, or are they concepts that emerge from deeper, more fundamental processes? Do they exist as we experience them, or are they simply constructs of our perception? One of the most provocative ideas about time comes from Julian Barber, a physicist and philosopher who has questioned the very nature of time itself. Barber argues that time, as we understand it, is not a fundamental feature of the universe. Instead, he suggests that time is an illusion, a human construct that arises from the way we perceive the world. According to Barber, all moments exist simultaneously as what he calls nows. Each moment is an independent, timeless snapshot of the universe, and time, in this view, is nothing more than our perception of the change between these moments. Barber's theory challenges the conventional understanding of time as something that flows continuously, from the past through the present and into the future. In his view, the flow of time is a product of our consciousness, not a fundamental property of the universe. Instead of seeing time as a river that flows from one moment to the next, Barber invites us to imagine that all moments in the universe exist together, side by side, in a vast collection of nows. The passage of time, then, is just a mental construct, a way we organize our experiences. This idea is deeply philosophical, but it also has serious implications for our understanding of physics. If time is an illusion, then our understanding of the laws of physics might need to change. For example, if time does not truly flow, then our usual understanding of cause and effect, where one event leads to another in a sequence, might need to be rethought as well. Barber's ideas suggest that the universe is timeless at its core, and that time itself is a byproduct of the way we perceive the world. But how does this fit with the scientific theories that have shaped our understanding of the universe, particularly Albert Einstein's theory of relativity? Einstein's work on spacetime fundamentally altered our perception of time, and his ideas continue to shape our understanding of the cosmos. One of the most important concepts in Einstein's special relativity is that time is not an independent universal flow, but is instead a dimension that is intertwined with space. Together, space and time form a unified entity known as spacetime. In this framework, time is treated as a dimension, much like the three dimensions of space. Just as we can move forward and backward in space, we also move forward in time. However, Einstein's theory shows that time does not operate in the same way for everyone. Time, in fact, can stretch and contract depending on the relative speed of two observers. This phenomenon, known as time dilation, shows that time is not an absolute fixed entity, but is relative to the observer's motion. According to Einstein, the faster an object moves relative to another, the slower its time appears to pass. This effect becomes particularly pronounced as objects approach the speed of light. For example, if you were travelling near the speed of light, time for you would slow down compared to someone who remains stationary. This is not just a theoretical idea. It has been experimentally verified in many ways, including the use of atomic clocks on fast-moving airplanes, which show that time slows down at higher speeds. In this way, Einstein's theory of relativity fundamentally changes how we understand time. It is not a fixed, absolute entity, but is instead a flexible, malleable dimension that depends on the observer's relative motion. This concept of time is radically different from the idea of time as a steady, unchanging flow. Instead, time is part of the fabric of space-time, which can be bent and stretched by gravity and motion. In addition to the relationship between time and motion, another important aspect of time is its direction. Why does time appear to move in one direction, from past to present to future? This brings us to the concept of entropy and the second law of thermodynamics, which has been central to our understanding of the arrow of time. The second law states that in any isolated system, the total amount of entropy, or disorder, will always increase over time. In other words, things naturally tend to become more disordered as time goes on. This increase in entropy gives time its direction, pointing it from moments of lower entropy, such as the Big Bang, to moments of higher entropy, such as the heat death of the universe. Sean Carroll, a theoretical physicist, has written extensively about the thermodynamic arrow of time, which is the idea that time moves in one direction because of the increase in entropy. Carroll argues that the flow of time and the direction we experience it is directly tied to the fact that the universe is constantly increasing in disorder. If the universe were in a state of maximum entropy, if everything were completely disordered, then time would cease to have meaning, as there would be no change or evolution to mark its passage. It's the continual increase of entropy, according to Carroll, that makes time feel like it's flowing forward, always towards greater disorder. This view links time and causality, our experience of one event leading to another, directly to the concept of entropy. The direction of time is not a mystical property, but a result of the physical laws that govern the universe. As we move through time, we move from states of lower entropy to states of higher entropy, creating a clear, irreversible flow from past to future. Without this increase in entropy, there would be no reason for time to flow in any particular direction. But the question remains, are time and causality truly fundamental properties of the universe, or are they simply byproducts of other deeper, more fundamental processes? In some ways, we are still grappling with this question. While time and causality certainly seem to be deeply embedded in our experience of the universe, some theories suggest that they may not be as fundamental as we think. For instance, in Barber's view, time as we experience it is not a fundamental feature of reality, but an emergent property of the way we perceive the universe. Similarly, the idea that causality is tied to entropy and the increase in disorder may suggest that causality too is not a fundamental law of nature, but a consequence of the second law of thermodynamics. In this sense, time and causality may not be universal, unchanging truths, but rather constructs that arise from the laws governing physical systems. As we explore these ideas, we are left with a deeper question. Does the universe truly operate in a way that depends on time and causality, or are these concepts simply ways we have developed to understand the flow of events? As our theories of space-time and quantum mechanics continue to evolve, we may find that the true nature of time and causality is even more elusive than we ever imagined. The more we learn, the more we may realize that time is not the fixed, flowing river we thought it to be, but something much more subtle and far more complex. When we think about the universe, we often picture vast stretches of space filled with stars and galaxies, all governed by the forces of nature. But at the very core of the universe's existence, at the very beginning, space and time themselves were born. One of the most fundamental questions in understanding the early universe is how gravity and space-time came to be, and how they shaped the world as we know it. These forces are so deeply embedded in our understanding of the universe that it's hard to imagine a cosmos without them. Yet the origin of both gravity and spacetime remains one of the great mysteries of modern physics. Lee Smolin, a theoretical physicist, offers a thought-provoking view on time in his work, The Life of the Cosmos. Smolin suggests that time itself may not have always existed, but instead emerged alongside the universe. This theory challenges the conventional idea that time is a constant, unchanging backdrop to all events. Instead, Smolin proposes that time was born with the universe, a crucial element that arose as space itself began to form. Smolin's theory is linked to his broader concept of cosmological natural selection, where the laws of physics, including time, are not fixed but evolve over cosmic cycles. In Smolin's view, universes might reproduce through black holes, with each new universe having slightly different physical laws. This means that time, as we understand it, could be a product of the universe itself, a force that came into being as space and matter began to emerge. Rather than being a universal pre-existing entity, time would be intricately tied to the birth and evolution of the cosmos. If Smolin's ideas are correct, the time we experience may not be as fundamental as we think, but rather an emergent property of the universe's creation. In this model, time is not a fixed framework that always existed. Instead, it is intimately connected with the creation of the universe itself, a concept that is both profound and unsettling, challenging our everyday understanding of what it means for time to exist. But time isn't the only fundamental concept that emerged with the universe. The very nature of space itself, the stage on which the events of the universe unfold, was also shaped by the early universe. Carlo Rovelli, an influential physicist known for his work on quantum mechanics and the nature of spacetime, offers a different perspective. Rovelli introduces the relational interpretation of quantum mechanics, which redefines our understanding of spacetime. According to Rovelli's relational interpretation, spacetime does not exist as a separate, independent entity, but rather as a product of interactions. In this view, spacetime emerges from the relationships between particles, energy, and forces. It is not a fixed backdrop against which events unfold, but a dynamic, relational structure that comes into being through the interactions of the particles and fields within it. This idea challenges the classical notion that space and time are absolute. Instead, Rovelli suggests that spacetime is not something out there, waiting to be measured, but something that comes into being as a result of the relationships between objects. Just as we might describe a social network by the relationships between individuals, Rovelli's relational theory suggests that space-time can be understood as a network of relationships between the elements of the universe, not a container within which these elements exist. The implications of this view are far-reaching. If space-time is relational, then it isn't something that exists independently of the objects within it. It is a fluid, dynamic entity that changes and adapts based on the interactions within it. This could provide a new way to think about the very origins of the universe, where space and time themselves arose from the interactions between fundamental particles, rather than being a pre-existing stage. It also has profound consequences for our understanding of gravity, which in general relativity is the curvature of space-time caused by mass and energy. If space-time is relational, gravity itself may be an emergent property of the relationships between matter and energy in the universe. While Rovelli's relational interpretation challenges the traditional view of spacetime, Nima Arkani-Hamed, a leading theoretical physicist, has proposed a completely different way of thinking about the fabric of spacetime. Arkani-Hamed is known for his work on the geometry of the universe, particularly his contributions to the study of higher dimensional spaces. In his work, Arkani-Hamed explores the idea that spacetime might have originated from higher dimensional spaces. According to his theories, the fabric of spacetime could be a lower dimensional manifestation of a higher dimensional reality. This means that the 3 dimensions of space and 1 dimension of time that we experience may be just a projection of something far more complex. In some models, such as string theory and brain theory, our universe might be a 3-dimensional brain embedded in a higher dimensional space. If spacetime originated from a higher dimensional reality, this opens up fascinating possibilities for understanding the universe. It suggests that our experience of space and time could be a mere shadow of a much more intricate structure that exists beyond our perception. Arkani-Hamed's ideas tie into the broader goal of understanding the unification of the fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, which are currently understood separately. By exploring the geometry of space-time in higher dimensions, Arkani Hamed and others hope to discover a deeper unified theory of physics. This idea also has profound implications for the early universe. If space-time originated from higher dimensional spaces, then the universe as we know it might have started as a kind of dimensional collapse, where higher dimensional spaces gave rise to the three-dimensional universe we experience today. The origin of space-time itself could have been a dramatic event, where the fabric of reality folded into the familiar dimensions we observe, a process that shaped the very nature of existence. Together, these theories from Smolin, Rovelli, and Arkani Hamed point to the possibility that both time and space-time are not fixed and unchanging. Instead, they may have emerged with the universe, shaped by the forces and relationships that govern its evolution. Time and space-time might not be the eternal, unmovable pillars of reality we once thought. Instead, they could be dynamic, evolving properties that arose as the universe itself came into being. This shift in thinking challenges many of our long-held assumptions about the universe. Rather than seeing gravity and space-time as eternal aspects of reality, we now have the possibility that they were born alongside the universe itself, emerging from a deeper, more complex process that we are just beginning to understand. The idea that space-time might have originated from higher dimensions, or that time itself is an emergent property of the universe's creation, forces us to rethink the very foundations of physics. As we continue to explore these ideas, we may discover that gravity and space-time are not as fundamental as we once believed, but instead are part of the universe's ongoing evolution, a story still being written as we search for answers to the deepest questions of existence. Imagine for a moment that everything you see, touch, and experience might not be what it seems. What if the three-dimensional universe around you, with its vast galaxies, stars, and planets, is actually a projection of something much more fundamental? A theory in modern physics suggests just this possibility, that our entire universe could be a hologram. At first glance, this may sound like science fiction, but it's a concept that has gained serious attention from some of the world's leading physicists. The idea of the universe as a hologram was first proposed by Juan Maldacena in 1997, and it's known as the holographic principle. According to this principle, the entire three-dimensional universe we experience could actually be a projection from a two-dimensional surface. This surface would be located at the event horizon of a black hole, essentially the boundary surrounding a black hole, beyond which nothing, not even light, can escape. To understand the holographic principle, think of a hologram. A hologram is a two-dimensional image that creates the illusion of three dimensions. In this analogy, the universe is like a hologram, where the seemingly three-dimensional world around us is actually a projection from the surface of a much lower dimensional reality. This raises the possibility that the entire universe, everything we experience in space and time, might be encoded on a two-dimensional surface, like a vast cosmic projection. This would mean that everything we see, every galaxy and star, might be an illusion created by the underlying information encoded at the event horizon of a black hole. This idea is not just a theoretical curiosity. The holographic principle has profound implications for our understanding of the universe. It suggests that what we perceive as the fundamental fabric of space and time might not be the real structure of reality at all. Instead, it could be a derived feature, a kind of projection emerging from a deeper, more abstract layer of existence. If this is true, it could completely change how we think about the nature of the cosmos. But the holographic principle is not the only theory that suggests our reality might be more complex than it seems. David Bohm, a renowned theoretical physicist, proposed an idea that aligns closely with the holographic view of the universe. Bohm's theory involves two layers of reality, the implicate order and the explicate order. According to Bohm, the implicate order is a deeper, more fundamental layer of reality from which everything in the universe unfolds. The explicate order, on the other hand, is the world we perceive, a world of distinct objects and events that seem to have their own separate existence. Bohm's implicate order is analogous to the idea of the holographic principle in that it suggests the universe we experience is not the whole story. Rather, it's a manifestation of a deeper, hidden reality that lies beyond our direct perception. The explicate order, the three-dimensional world we experience, is like the unfolded projection of the implicate order. Just as a hologram appears to have depth and volume, but is actually a two-dimensional image, the universe we experience might be a projection of a deeper, more fundamental reality that we can't directly access. Bohm's theory challenges our conventional understanding of space and time. In his view, the universe is not made up of separate, independent objects, but is instead a unified whole with everything interconnected. The division between objects and space is an illusion. Just as in a hologram, the parts of the image are inseparable from the whole. In this framework, everything in the universe, from the smallest particle to the largest galaxy, is part of a larger, interconnected system that can only be understood as a whole. This idea has fascinating implications for how we think about the origin of the universe. If the universe we see is simply the projection of a deeper reality, then it's possible that the true nature of the cosmos lies beyond our perception, waiting to be uncovered by deeper theories. What we experience as space, time, and matter may be mere shadows, reflecting a reality that is far more complex and profound than we can currently imagine. The holographic principle and Bohm's implicate order both challenge the traditional view that space and time are fundamental aspects of reality. Instead, they suggest that what we experience as the fabric of the universe may emerge from deeper, more abstract processes. These ideas push us to reconsider not just the nature of the universe, but also the very meaning of existence. One of the most exciting possibilities that arises from these theories is the idea that black holes could be the key to understanding the holographic nature of the universe. The event horizon of a black hole, the boundary beyond which nothing can escape, might contain all the information about everything that falls into it. This means that the entire universe could be encoded on the event horizon of a black hole, and what we perceive as the three-dimensional world could be a projection of that information. This idea leads to a deeper understanding of the nature of nothing, the idea that what we think of as empty space might be filled with information, just waiting to be uncovered. But how does this idea fit with the origins of the universe itself? If the universe is a hologram, then it might not have the simple, linear history that we think. Instead, the holographic model suggests that the universe's existence might be tied to deeper, more abstract principles that we have yet to fully understand. The origins of the universe, in this view, could be linked to the fundamental structure of spacetime itself, something that transcends the familiar three-dimensional reality we experience. In this sense, the holographic principle offers a new way to think about the creation of the universe. Instead of a simple Big Bang event that marks the beginning of everything, the holographic view suggests that the universe's birth might be connected to the underlying structure of reality, encoded on a two-dimensional surface. This could mean that the entire history of the universe, from the Big Bang to the present day, is part of a deeper process that transcends the linear flow of time. The holographic principle has the potential to reshape our understanding of existence itself. It forces us to rethink what we mean by reality, suggesting that the universe we see and experience is not the whole story. Instead, it might be a projection, a kind of cosmic illusion, that emerges from a deeper, more fundamental layer of reality. Just as a hologram creates the illusion of three-dimensional depth from a flat surface, our three-dimensional universe could be a projection of a deeper, more complex reality that we are only beginning to understand. The idea that the universe is a hologram raises profound questions about the nature of space, time, and existence. It challenges us to consider that what we experience as reality might be just one layer of a much more intricate and mysterious cosmos. As we continue to explore these ideas, we may uncover new insights that not only change our understanding of the universe, but also reveal the true nature of existence itself. For as long as humans have looked up at the stars and pondered the origins of the universe, one fundamental question has remained. Why is there something rather than nothing? It's a question that stretches beyond the boundaries of science and into the heart of philosophy. Does the universe need a cause? Or could it be that the existence of the universe itself is simply a brute fact, something that exists without any explanation? To grapple with this, we must explore not only the origins of the universe, but also the very nature of creation, causality, and the possibility that nothingness might be an active part of the cosmic process. Alfred North Whitehead, a British philosopher and mathematician, introduced a deeply influential perspective on reality through his process philosophy. According to Whitehead, reality is not a static, unchanging entity, but a constantly evolving process, a becoming rather than a being. For Whitehead, All things are in a constant state of flux, with each moment giving rise to the next. This dynamic, ever-changing process suggests that the universe is not a finished product, but an ongoing event, where existence itself is constantly unfolding and being shaped. In Whitehead's view, even nothingness is part of this process. He suggests that nothing is not simply an absence, but rather an active, dynamic state that interacts with the ongoing becoming of the universe. Instead of seeing nothingness as a void or a mere lack of being, Whitehead presents it as a necessary component of the process of creation. In this framework, creation itself is an ongoing, eternal act, where each new moment is born from the interactions and processes of those that came before. This idea challenges traditional concepts of creation, which often envision the universe as having a clear beginning, a point where everything started. In Whitehead's philosophy, the universe doesn't begin in the conventional sense. Instead, it is in a state of continuous creation, where past moments influence and give rise to future moments. This view suggests that the universe is not a product of some initial act of creation, but an ongoing, dynamic process that is ever in the act of becoming. This perspective invites us to reconsider the idea of causality, not as a linear chain of events, but as an interconnected web of processes that shape and reshape the fabric of reality. Moving beyond the realm of process philosophy, we can turn to the ideas of Emmanuel Levinas, a 20th century philosopher whose work focused on ethics, existence, and the concept of the other. For Levinas, the very act of existence is deeply tied to the ethical relationship we have with what he calls the other, that which is beyond us, beyond our understanding, and beyond our control. Levinas suggests that existence is not just about being, but about an ongoing ethical relation with something greater than ourselves, something that cannot be fully understood or contained. In this sense, Levinas presents a radically different view of the universe's existence. Rather than seeing the cosmos as a result of some impersonal mechanical cause, he argues that existence itself is an ethical act, a response to the other. This other is not just another being or entity, but the very presence of the unknown, the unknowable. In Levinas's framework, the act of existence is a kind of ongoing response to this mysterious other, a continual process of becoming that cannot be fully explained or reduced to physical laws. For Levinas, the question of why the universe exists is not merely a question of causality in the traditional sense, but a question of relationship, a relationship that extends beyond the realm of science and into the realm of ethics. The existence of the universe and the experience of being is tied to a deeper, unanswerable question of how we are related to what is beyond our comprehension. In this view, creation is not just a cosmic event, it is a moral and existential process, an ongoing engagement with the unknown. Now, if we shift our focus to the nature of causality itself, we enter the realm of Peter van Inwagen, an American philosopher who is known for his work on ontological arguments, the philosophical study of being and existence. Van Inwagen's thoughts on causality and existence challenge the idea that the universe must have a cause in the traditional sense. He presents the idea of brute facts, which are facts that simply exist without explanation. According to van Inwagen, the universe itself might be one of these brute facts, an ultimate inexplicable fact that does not require a cause. This perspective offers a challenge to the classical view of causality, where every event must be traced back to a prior cause. Instead, van Inwagen suggests that some things, like the universe itself, may simply exist without needing an explanation. This view places the universe's existence outside the chain of causes and effects that we are so familiar with. It raises the possibility that existence itself is a fundamental feature of reality, not the result of a causal process. Van Inwagen's concept of brute facts does not mean that the universe is a random or chaotic place. Rather, it suggests that the universe might simply be a given, a fact that exists because it does, without needing any further explanation. This idea has profound implications for how we think about the origins of the universe. It implies that the universe might not need to be created by some external force or event. It could simply exist as a fundamental feature of reality, independent of any prior cause. Taken together, the ideas of Whitehead, Levinas, and van Inwagen present a radically different view of the universe's existence. Whitehead's process philosophy suggests that the universe is an ongoing, dynamic process, with time and causality emerging as part of this unfolding reality. Levinas presents existence as an ethical act, where being itself is a response to the other, an engagement with something beyond our understanding. Van Inwegen challenges the need for a cause at all, suggesting that the universe may simply be a brute fact, existing without explanation. These philosophical perspectives invite us to think about the universe in ways that go beyond the traditional scientific view of cause and effect. They encourage us to ask deeper questions about the nature of existence, the role of causality, and the possibility that the universe might simply be, in all its complexity, a fundamental fact of reality. Whether the universe is a product of an ongoing process, an ethical relationship with the unknown, or a brute fact that simply exists, these ideas push us to reconsider the very foundations of our understanding of existence. As we ponder these questions, we are reminded that the universe, with all its mysteries, may not be as easily explained as we once thought. The question of why there is something, rather than nothing, might not have a simple answer. Perhaps in the end, the very nature of creation is something that transcends cause and effect, something that lies beyond our ability to fully comprehend, but is no less a part of the deep, existential mystery of the cosmos. The question of existence is perhaps the most profound question that humanity has ever grappled with. What does it mean for something to exist? How do we come to be? And what role does consciousness play in the grand cosmic picture? These questions stretch beyond science and enter the realm of philosophy, where ideas about existence, consciousness, and the infinite are not just speculative. They form the very foundation of our understanding of reality. One of the most intriguing theories about the relationship between consciousness and the universe comes from David Bohm, a physicist known for his deep work on quantum theory and the nature of reality. Bohm proposed that the universe is not composed of separate independent parts, but rather is a unified whole. He suggested that what we perceive as separate objects and events are merely aspects of a deeper implicate order, a hidden layer of reality from which everything unfolds. In this view, the universe is not a static, unchanging entity, but a continuous process of becoming. Bohm's perspective challenges the classical view of reality as a collection of fixed objects. Instead, he argued that reality is dynamic and constantly evolving, with everything in the universe interconnected. This interconnectedness suggests that consciousness itself might not be a mere byproduct of brain activity, but could be intimately tied to the fabric of the universe. Bohm's ideas hint at a universe where the active nature of consciousness plays a role in shaping reality. Rather than seeing consciousness as something that emerges only within the brain, Bohm's framework suggests that consciousness could be a fundamental aspect of the universe, a property woven into the very structure of existence. Just as particles and forces arise from the implicate order, so too might consciousness emerge as a dynamic, active force that shapes the ongoing process of creation. Building on this idea, Ruth Kastner, a physicist and philosopher, has explored the idea of active consciousness in the context of quantum mechanics. Kastner's work suggests that consciousness is not just a passive observer of the universe, but an active participant in the process of creating reality. In her view, consciousness is intricately tied to the quantum world, and its involvement is essential for the unfolding of the universe. Kastner argues that the act of observation itself, a conscious act, brings potential realities into existence, determining the course of events and shaping the way the universe unfolds. This view has profound metaphysical implications. If consciousness is actively involved in the creation of reality, then the very act of awareness becomes a fundamental aspect of existence. The universe, in this framework, is not a pre-existing fixed structure, but one that is continuously shaped and formed by conscious experiences. In this way, consciousness doesn't just emerge from the physical world, it is woven into the very fabric of reality, actively participating in the process of becoming. But what does this mean for the nature of time and the universe itself? Berenice Carrion, a philosopher who has studied existential consciousness, proposes that reality is a continuous process of becoming, rather than a fixed state. Carrion's perspective suggests that the universe is constantly in a state of flux, with existence unfolding moment by moment. Time, in her view, is not a linear progression from past to future, but a dynamic flow that emerges from the continuous interaction of consciousness with the world. According to Carrion, our experience of reality is shaped by the conscious acts of perceiving, interpreting, and interacting with the world around us. Consciousness, she argues, is not something that merely reacts to the world. It is an active participant in the creation of reality. This view of consciousness as an active, creative force challenges the idea that the universe is a machine that runs according to fixed laws. Instead, it presents the universe as a living, evolving system, shaped by the ongoing interplay between consciousness and existence. The idea that consciousness is integral to the process of creation is not limited to quantum mechanics or the implications of the holographic principle. It extends to the very way we understand existence itself. If consciousness is an active, dynamic force, then the universe is not something that simply exists as a static backdrop to our lives. It is an unfolding reality, one that is continuously shaped by the conscious experiences of those who perceive it. This brings us to the question of the infinite, an idea that has intrigued philosophers for centuries. If reality is constantly becoming, then what role does the infinite play in this process? Immanuel Kant, the German philosopher, argued that our understanding of the infinite is limited by the very nature of our consciousness. For Kant, the infinite is not something that can be fully grasped or understood by the human mind. It is an idea that points beyond our cognitive capabilities, a concept that transcends our experience of time and space. However, other philosophers and physicists have suggested that the infinite may not be beyond our reach. Georg Wilhelm Friedrich Hegel, for example, argued that the infinite is not something separate from the finite, but is instead inherent in the unfolding of reality itself. In this view, the infinite is not a distant abstract concept. It is part of the very process of becoming, an aspect of the ongoing evolution of existence. For Hegel, the infinite is present in every moment of creation, woven into the very fabric of reality as it unfolds. In a similar vein, the concept of the infinite has been explored by modern cosmologists. The multiverse theory, for example, posits that our universe is just one of many in a larger, infinite multiverse. According to this theory, the laws of physics that govern our universe may be just one set among countless others, each with its own set of possibilities and realities. The multiverse, in this sense, offers a vision of infinite potentialities, where the universe we inhabit is just one small part of an infinite cosmic landscape. This view of the infinite challenges our understanding of reality as a fixed, unchanging entity. If the universe is part of an infinite multiverse, then existence itself becomes an ongoing process, one that unfolds across multiple dimensions and realms of possibility. The infinite is not a distant abstraction, but a fundamental aspect of reality, something that is present in every moment of creation. As we contemplate the nature of existence, consciousness, and the infinite, we begin to see how deeply interconnected these ideas are. Consciousness is not just a passive observer of reality. It is an active participant in the ongoing process of creation. The universe is not a fixed, static system, but a dynamic, evolving process, one that is shaped by the conscious experiences of those who perceive it. The infinite is not a distant concept, but an intrinsic part of the ongoing unfolding of reality itself. Together, these ideas offer a vision of the universe that is not fixed, but alive, constantly evolving and shaped by the interplay between consciousness and existence. In this view, the universe is not just something that exists independently of us, but something that is co-created through our conscious experiences. The mystery of existence, then, is not something that we can fully grasp through logic alone. It is something that unfolds in the continuous dance between consciousness, time, and the infinite, an ongoing process of becoming that shapes the very fabric of reality itself. As we wrap up this journey through the many questions and theories that surround the mystery of existence, it's clear that the universe, its origins, and the nature of reality itself are far more complex and enigmatic than we often give them credit for. From ancient philosophy to cutting-edge physics, we've explored a wide range of perspectives, each offering its own insights into the question, why is there something rather than nothing? We began by diving into the nature of nothingness itself. Philosophers and physicists alike have long wrestled with the concept of non-existence, from Heinz-Dieter Ruder's exploration of quantum vacuum fluctuations to John Archibald Wheeler's idea of a participatory universe. As we learned, what we think of as nothing may not be as empty or passive as we imagine. It's a concept that is actively shaping the universe, even in its apparent absence. From quantum fields to the relationship between consciousness and existence, we saw that the very fabric of the universe may be much more dynamic and interconnected than we perceive. We then explored the possibility of a pre-Big Bang state, considering theories like Roger Penrose's conformal cyclic cosmology, which proposes that the universe may go through infinite cycles of birth and rebirth. Lee Smolin's cosmological natural selection theory further added to this, suggesting that the laws of physics might evolve through a process of cosmic reproduction, not just randomly, but through a selection process that favours the formation of black holes and, perhaps, life itself. The multiverse theory, too, introduced by thinkers like Andrei Linde and Alexander Vilenkin, provided a cosmic landscape where the Big Bang is not a unique event, but part of an eternal process of inflation, with countless universes spawning in an infinite cycle. In discussing the nature of time and causality, we saw how modern physics continues to challenge our traditional views of these concepts. Julian Barber argued that time is an illusion, and that all moments in the universe exist simultaneously as nows. Hermann Minkowski reshaped our understanding of time by combining it with space to form space-time, where time is not separate from the physical world, but intricately linked to the fabric of the universe itself. Meanwhile, Sean Carroll helped us understand the thermodynamic arrow of time, where the flow of time is tied to the increase of entropy, giving us a clear direction, from lower entropy to higher entropy. From there, we ventured into the strange world of black holes and their potential to unlock the deepest mysteries of the universe. Roger Penrose's ideas on black hole singularities as potential gateways to other universes gave us a glimpse into the possibility of cosmic recycling, while Stephen Hawking's information paradox forced us to confront the question of whether information can truly be lost inside a black hole. The holographic principle, introduced by Juan Maldacena, suggested that our entire universe might be a projection from a two-dimensional surface, changing the way we think about space, time, and existence itself. As we delved into the question of the universe's fine-tuning, we encountered the anthropic principle, first discussed by John Barrow and Frank Tipler. The universe, as it turns out, may not have emerged by random chance, but rather with conditions that are remarkably conducive to the emergence of life. This prompted us to consider ideas like David Deutsch's multiversal fine-tuning, which suggests that our universe's apparent perfect fit for life could simply be a consequence of a much larger multiverse where different laws of physics give rise to different possible realities. Through it all, we return to the deeper question of consciousness and its connection to the cosmos. Could consciousness itself play a role in shaping the universe? David Chalmers raised the hard problem of consciousness, asking why and how subjective experience arises from physical processes. Giulio Tononi's integrated information theory suggested that consciousness might not be an emergent property, but a fundamental aspect of reality, intertwined with the fabric of existence itself. Roger Penrose took this further, connecting consciousness to quantum processes in the brain, proposing that consciousness might even be linked to the very processes that govern the universe. Bernardo Kastrup suggested that consciousness is not just a byproduct of brain activity, but the very substance of reality, suggesting that the universe itself could be a manifestation of consciousness. We also touched upon the dynamic nature of creation and causality. Alfred North Whitehead proposed that reality is in a constant state of becoming, where nothingness is not the absence of existence, but part of the ongoing process of creation. Philosophers like Emmanuel Levinas and Peter van Inwagen further questioned the need for a cause for the universe, with van Inwagen proposing that the universe might be a brute fact, existing without a need for an external cause, challenging the very concept of causal necessity. Ultimately, each of these theories presents a different perspective on the mystery of existence, but they all share one thing in common. They reveal how little we truly understand about the nature of the universe and our place within it. Whether we look at the fine-tuning of the universe, the role of consciousness, the birth of time, or the mysteries of black holes, we are left with a profound sense of wonder and a realization that the answers to these questions may be elusive. Why is there something rather than nothing? The more we explore, the more we realize that the question itself might be far more complex than we can grasp. Is the universe a product of chance, necessity, or design? Does consciousness shape reality, or is it just an emergent property of the brain? These questions don't have simple answers, and perhaps they never will, but that does not diminish their importance. The pursuit of these answers is what drives science and philosophy forward. pushing the boundaries of what we know and deepening our understanding of existence itself. As we stand at the edge of this vast cosmic mystery, we must remember that the search for answers is as important as the answers themselves. Even though we may not yet understand why the universe exists, the very act of asking, exploring, and reflecting keeps us moving forward, deepening our connection to the cosmos and to each other. The journey of discovery continues, and as we unravel the mysteries of existence, we're reminded of the vastness of the unknown and the importance of embracing the questions that shape our understanding of life, the universe, and everything within it.